All right, lesson 7, half-life. So half-life, which has the symbol T with a little 1/2 next to it, is the time for half of the radioactive nuclei in any sample to undergo radioactive decay. So here's an example of what that means. So polonium-211 is a radioactive nucleus. It undergoes alpha decay, and when it does this, it becomes lead-207. And polonium-211's half-life is approximately 0.5 seconds. So suppose here that we have a sample of polonium-211. So this is our sample. And inside of that sample, each red box represents a polonium nucleus, and any white boxes represent lead nuclei. So here, currently, this is all in the form of polonium, so there's no lead yet. So at the beginning, which we're calling time 0, there's actually 2,500 polonium nuclei in there. And so there's 100% of the polonium nuclei remaining here. After one half-life has gone by, so remember we said the half-life is 0.5 seconds, so now one half-life has passed, which means the time on the clock is 0.5. Only half of the polonium are left. So that's what half-life means. It means if you wait for one half-life to pass, half of your original nuclei have decayed. And so half of 2,500 is 1,250. And that means that if we started with our sample containing 100% of polonium, now it's only 50% polonium. So if you look at your sample here, about half of the boxes now are polonium, and the other half have turned into lead. And we can keep going like this. So if we wait now for 2 half-lives to go by, so now 1 second has passed, the amount of polonium has halved again. So 625 is half of 1,250, which means that now we only have 25% of the polonium that we started with. And we can do it again. You can look at the chart there. And so to summarize, this is what you need to fill in your notes. So after 0 half-lives have passed, which is just at time 0, we had all of our polonium. After 1 half-life, 2, 3, and 4 half-lives, we can see what's going on. So I encourage you to pause the video, look at the chart, just make sure it makes sense to you. Alright, so introducing the first formula for half-life. So it's this formula here that has a box around it. Just be aware that's not on the formula sheet, so you will need to memorize that one. N stands for the number of half-lives that have passed, and that is a unitless value. T is the total time that has gone by, and T1/2 is the time for 1 half-life. Now, there's no specified units for T and T1/2. Just make sure you use the same units for both. So if you're going to work in seconds, then both of these things here have to be in seconds. Or if you're going to work in years, then they both have to be in years. Alright, here's the half-life formula. This one is on the formula sheet. So just be careful because here we have an uppercase N and a lowercase n, and they are 2 different things. So lowercase n, as we said on the last slide, is the number of half-lives that have passed. Uppercase N with a little 0 next to it is the original amount. Now here amount can be measured in different units. So sometimes it's measured in number of atoms, sometimes it's measured as a mass, so grams, kilograms, micrograms, or sometimes it's measured in something called activity, and we'll come back to what activity is later on in the lesson. And capital N, without the 0, is the amount remaining after lowercase n half-lives have passed. So here's an example of how to use those formulas. So a 100-gram sample of iodine-131. So this is telling us we're starting with 100 grams. So the original amount is 100 grams. This undergoes beta-negative decay with a half-life of 8 days. So T1/2 is 8 days. And then it says determine the amount remaining. So amount remaining is uppercase N. after 80 days. So the time has gone by and 80 days have passed. So first thing that we're going to do is we're going to calculate little n, which is the number of half-lives that have passed. And remember, the way to do that is to take the total time and divide it by the time for one half-life. So the total time here is 80 days, and the time for one half-life is 8 days. So that means 10 half-lives have passed. Now what we're going to do is we're going to plug our numbers into the half-life formula, which looks like that. So we're going to take the original amount, which is 100 grams, and multiply this by 1/2 to the power of 10. And that gives 0.0976 ... And the units of this are going to be the units of whatever the amount is. So because the amount was measured in grams, the units of my answer is also in grams. And so to two significant digits, 0.098 grams is the amount of iodine 131 that remains after 80 days. Okay, let's do another one. Example 2. A sample of polonium-210 with a half-life of 138 days, so T1/2 is 138 days, has a mass of 8.5 milligrams 15 days after it was prepared. So T is 15 days. Now be careful here. It's not saying that the polonium sample had a mass of 8.5 when it was first prepared. So 8.5 is not N0. Instead, it's saying after some time has already passed, that 8.5 milligrams is the amount that remains. So capital N is 8.5 milligrams. And then it says calculate the sample's original mass, meaning we want to find out N0. So like before, let's calculate the number of half-lives again by doing T over T1/2. So that's going to be 15 days over 138 days. And that's 0.10 ... Now we'll write down our half-life formula. So there it is. And we're going to rearrange for N0 for the original amount. So N0 is just going to be N divided by 1/2 to the power of little n. So this is just going to be 8.5 milligrams over 1/2 to the power of 0.10 ... Make sure that you don't round yet. And that gives me 9.165, but to two significant digits, this is going to be 9.2 milligrams. All right, next, activity. So becquerels are the unit that we use when we talk about activity. So 1 becquerel means 1 decay per second. So if I had something that was 10 becquerels, so if I said it had an activity of 10 becquerels, that would mean that it is decaying 10 times every second. Now, activity is directly proportional to the amount of the substance. So imagine we have thorium-227. If we have 50 grams of thorium-227, that will have half the activity of 100 grams of thorium-227. So the idea is if you have half the amount, then you will also have half the activity. Okay, example 3. Use the graph to determine the half-life of the radioactive sample. So here we have activity on the y-axis and time on the x-axis. And here's how you're going to use a graph to find the half-life. So first of all, look for the y-intercept. So here, the y-intercept is 200. So the idea is the original activity of this sample is 200. What we want to do is we want to figure out how long it takes for the activity to go down by half. So half of 200 is 100. So what we'll do is at 100, we'll see how much time it took to get there. So to reduce the activity by half, to go from 200 to 100 becquerels, that took 3 days. So it's looking like the half-life is 3 days. Now what I would recommend though is don't just do this in one place on the graph, do it again and then average the values together. So what I mean by that is currently we're looking at something that has an activity of 100. Half of 100 is 50. So I'm going to go down to 50 and I'm going to do this again. And I see, now I didn't draw that very well, but if I was doing this with a ruler on paper, it would end up being at 6. And I know that because I did this on paper earlier. There, that looks a bit better. So again, okay, now I find that the half-life went from 3 days to 6 days. So 3 days to 6 days, that's also just a difference of 3 days. And then what I would do is I would average these together. Now in this case, they're the same value, so it's easy to see that the average is just 3 days. But sometimes when you do this, depending on if the graph is perfect or not, you might get slightly different values for the different half-lives. So just make sure you do it twice or more and then just average them together. All right, example 4. Phosphorus 32 with a half-life of 14 days is used to label DNA. A fresh sample of phosphorus 32 has an activity of 9132 counts per minute. Sometime later, its activity is only 2283 counts per minute. At this time, how old is the sample? All right, so the half-life is 14 days. A fresh sample, so that means something to do with the original amount, has an activity of 9132 counts per minute. Now we're not going to call that becquerels because becquerels is counts per second. So counts per minute isn't really becquerels. It's still an activity. It just has different units. Sometime later, its activity is only 2283 counts per minute. And we want to know how old is the sample. Okay, now if we write down our formula, the idea here is if we can find out what little n is, then we can use little n to solve for t, because we also have this formula here. The problem is, in Physics 30, you're not expected to know what a logarithm is. So if you've taken Math 30 already, you might know that you can solve for little n here using a log. We don't require you to do that in Physics 30. So I'm not going to solve it the way that you would if this was math class. Instead, in Physics 30, here's how they expect you to tackle a question like this. So basically, you write down 9132 because that's the original amount. Okay, so when little n is 0, no half-lives have passed yet, the amount, or the activity, same idea, is 9132. Now what you're going to do is you're going to say, okay, after 1 half-life, what is the activity? And remember that every time 1 half-life goes by, the amount is going to go down by half. So I'm just going to divide 9132 by 2. So after 1 half-life, the activity is 4166. And then I do this again. So after 2 half-lives, now the amount is 2283. So each time that I do a new row, I'm just taking the value from directly above and I'm dividing by 2. So I can do this again. And I'll do it one more time. There. So going back to the question for a second, okay, we want to know how old is the sample at 2283 counts per minute. Well, 2283 shows up right here. So I didn't actually need to do as many rows of the table as I did. So I know just from looking at this chart that 2 half-lives went by. So now, because n is t over t1/2, I can just solve for t by doing n times the half-life. So this is just going to be 2 times the half-life, which was 14 days. And 2 times 14 days is 28 days. So this sample is 28 days old. Now, if you want to solve this question in a different way, you can feel totally free to do that. But in Physics 30, all of the questions like this one, so if it's a question that asks you to solve for either little n or t, it's always going to involve nice numbers. And what I mean by nice numbers is you'll always be able to solve it just by making a chart like this. Okay, example number 5. Calculate the percentage of a substance that remains after 400 microseconds if its half-life is 170 microseconds. Okay, so the difference with this one is that this one talks about percentage. So if you get a question that talks about percentage, here's what you do. So to begin with, you're going to start with 100%. And then you want to know what percent is left after a certain amount of time. So the time here is 400 microseconds, and time 1/2, which is the half-life, is 170 microseconds. So I'm going to just begin by calculating the number of half-lives that have gone by. So I'm just going to do 400 over 170. And that gives 2.35. I'll just write that as 2.3 ... half-lives. And then we just plug this into the formula just like before. So n is NO times 1/2 to the power of little n. So NO is 100%. And then we're doing 1/2 to the power of 2.3 ... And this gives me 19.57 ... percent. And so for my final answer to 3 significant digits, 19.6% is the answer.